Looks like we made it, folks. Just about there, and week 7 is over. Just have to get through today, and tomorrow we're going to be in midterm week. Well, any questions, folks, before we get started today? Okay, well, not too much major things going on in the announcement so far, but let's run through them anyway. We're just about ready to finish section 9.1. We have a pretty long last example to get through, but it's required just so that you see what's going on our problem 21 right here. So that's going to support that last problem, the homework questions. Then, well, 9.1 is a weird section. We're just talking about how to build a differential equation, how to model reality using these things to the best of our ability, and how to check if we have a solution or not. But in section 9.3, we're going to change gears and actually start solving a certain class of differential equations. Those are going to be the ones that are referred to as separable. So that'll be a kind of interesting adventure. Then we're not going to cover all parts of chapter 9. We already skipped section 9.2. We'll skip 9.4 and get into section 9.5 on linear equations. So 9.3, 9.5 gives us a pretty wide class of different kinds of differential equations you can solve to get started working in the sciences. So down below then, that means next week is going to be pretty much a normal week as usual, but our exam 2 is coming up. And just like for exam 1, I have a certain cutoff before we allow more material to end up onto exam 2. Whatever we get to on the end of this week, potentially if we finish section 9.5, that's going to be the last section that's actually on the exam. That way you'll have the opportunity to work the homework problems, get your questions answered, get your homework turned back, that kind of stuff, before those actual sections are on the second exam. So looking through Moodle, let's take a look at exam 1. Exam 1 ended on section 7.5. That means exam 2 is going to pick up with section 7.7. Nothing too major on that. That's the one on approximate integration, trapezoid rule, midpoint rule, Simpson's rule. Probably just one question from there. Then section 7.8. We did take a lot of time here. There's 2 kinds of improper integrals, so you should expect an improper integral type 1 and improper integral type 2 in that section. Then we get into these sections. These are the model or the applications of integration. I'm thinking probably one, either an arc length or surface area problem. I'll just randomly choose one or the other, flipping a digital coin essentially. These are pretty long integration problems, so doubling up on it is just a little bit too much, I'd say. Finally, in section 8.3, we're not going to ask the hydrostatic force on the exam. It's going to be a question about centroids. So there could be some really fast concept questions where it's just coordinates on an XY plane, or it could be a full problem where you're finding the actual centroid coordinates. Depending on how long the exam is, I might make those partial problems where you're just finding the first coordinate or the second coordinate, for example. Then I'm not too sure if very much here fits an exam setting, but there could be a really fast concept question in 9.1 where I give you a differential equation, I give you a function, and you just check if it's a solution or not. Here, we'll be solving a differential equation, so probably 1 or 2 problems from here. These are usually pretty short sections. So that's pretty much what the exam is going to look like. Again, we'll have better information once this gets filled out this coming weekend. Any questions at all, folks, with the announcements? Okay, well, let's get started. We left off section 9.1 with this problem right here. And I imported from the Calculus 1 notes the increasing-decreasing test, which seems kind of curious at first, but that's one of the cool things about differential equations. If you're dealing with the first-order differential equation, that means the highest order derivative that occurs in your equation is the first derivative, like we have right here. And the increasing-decreasing test is talking about the first derivative. So that's kind of neat. We can now use information about the increasing-decreasing test to say something about the function v here. Who knows what this is? Let's read through the context really carefully. It says the Fitzhugh-Nagumo model for the electrical impulse of a neuron. So this is talking now about how your brain works. It's kind of cool, just a giant calculator. So the electrical impulse for a neuron states that in the absence of relaxation effects, I'm not sure what that is, but in the absence of relaxation effects, the electrical potential in a neuron, V of t, obeys this differential equation. And the potential in a neuron Well, electrical potential could be positive or negative, so could this value right here. So we're modeling how your brain fires, causing those electrical potentials, giving information across your neurons. And they're saying that this is the model of how that actually all works. Doesn't mean it models reality perfectly, but this is a great start to understanding these electrical impulses. So again, that's kind of cool. It's how your brain works. So we're really digging deep under the hood on this thing. Here they say A is a positive constant. I'm not too sure how they find it, but they must verify something experimentally and plug in the constant. Constrained between 0 and 1. And just to make this problem a little bit more concrete, kind of similar to the homework question, I personally chose a value 1/2. I don't know what that would really say about the model, but it takes this model, takes a 1 plus A, it turns it to a 3/2, and takes a plus A and turns it to a plus 1/2. So we'll work on that model there officially. Might as well change over the color coding with the highlighter. Part A is asking for the equilibrium solutions. And what we mean by that is an equilibrium solution occurs whenever the derivative of that function v comes out as 0. So in other words, anytime you see this in a problem, it means we're solving dv dt set equal to 0. So that's our equation to work with on this problem. Any questions at the moment, folks? Okay, solving that equation is not too bad. Let's first substitute in this whole function in for dv dt. We're solving negative v times v squared minus 3/2 of v plus 1/2 set equal to 0. We have one solution already, that's v equals 0 coming from this factor, but we need to do a fuller factorization of this thing in the middle. This is a little bit easier to factor if we first factor out 1/2 from that entire group. So this will turn into negative v times 1/2, that's the half factored out. If you factor out a half, it means you're dividing by a half essentially, and that would give us multiplication by 2 right here. So do 2v squared. This will turn into negative 3v plus 1. I think it's easier to visualize distributing 1/2 back inside. We give you v squared, a cancellation, negative 3/2 v plus 1/2. That's kind of a weird way to factor stuff out. Then, once we get to that step, I need to recall the right-hand side is still set equal to 0, so that's a good thing to remind ourselves. But that polynomial now factors a lot nicer. So this becomes negative v over 2. Factorization going this way with a 2v and a v. Then we need double negatives to get a negative 3v. And a 1 and a 1 should do the job. Let's just double check real quick. Multiply here to here, it's negative 2v. Here to here is negative 3v. So we do hit our target, the middle term of negative 3v. So when it comes to finding the equilibrium solutions, that's all we're doing. We're wondering for what value of v does the derivative become 0. Coming down here, we can now say, once we get an official pen going, the equilibrium solutions are from this term right here. This solves the equation when the electrical potential V is 0. So if we have V equals 0, we refer to that as our equilibrium solution. That's when this derivative up here is 0, which means no change. Next one comes from here. This would be V equals 1/2 to make a 0 occur. And the last equilibrium solution is when V is exactly 1. Well, we got it, folks. Those are the equilibrium solutions to this derivative. Just when the derivative is 0 is what we're producing. Oops, didn't mean to scroll up that way. There we go. So when you go to do this on your problem, that's essentially all you're looking for right here. Next thing we'll do is actually take this increasing decreasing test and find for what values of V is V increasing. That's kind of a confusing question. But keep in mind, think of this as the derivative of v. Then over here, if the derivative of v is positive, That means V itself is increasing. So F is playing the role of V in this increasing decreasing test from Calculus 1. And finding the equilibrium solutions, that's actually your part C on your real homework question. But I think that's a good part A, truly, because this is the first thing you'd want to do if you're solving that kind of inequality. We have a derivative, which we have put into this nice factored form. So to solve these inequalities, we'd probably want to do something like this. So this is a V-axis for the, let me make sure I'm saying this right. This is for the electrical potential in the neuron. I'll just say electrical potential, V. We put down the equilibrium solutions. Here's one at 0. There's one at 1/2. One at a +1. And then we can partition this V-axis into 4 different regions now. We have the infinitely long region, -infinity to 0, a couple finite regions here and here, and one more infinite region from 1 to infinity. So we need to find out where is f prime greater than 0, but that's going to be the dv dt, this function up here. So for each one of these, we'll say dv dt and find out if it's positive or negative. Which means this could be a pretty long problem, but there is a massive hint on how this can all be put together. When we look at this fully factorized equation here, we have only degree 1 on every single term. More critically, the degree is odd, power 1 here, here, and here. If these are all odd degrees, it means the signs of every single one of these regions is going to interchange. So if that's positive, the next one's negative, and vice versa. We just have to test one region. But watch out for problems. I didn't assign any, but if there's a power 2 here, that goes out the window. Something can go positive and positive across a value where there is an even exponent, for example. So let's test out just this one value. We can either pick the far left or the far right. Maybe this is a little bit nicer, less negative signs. We're going to test at a value of 2. That's our derivative right here. So in Leibniz notation, we would say dv dt. We're referring to f prime essentially, but in Leibniz notation, and the function is v, not f. We're evaluating at the test point, v equals 2. Then when v is 2, right where the red dot is, we're plugging in a 2. So we'll get -2/2. On the next term, 4 minus 1 for a +3. On the next term, 2 minus 1 for a +1. And the whole thing is negative, less than 0. That starts the pattern. So that means way out here, the one we picked, we have negative. What does the increasing decreasing test then say? It says, well, if your derivative is negative on an interval, then the function is decreasing on that interval. So we are decreasing here. Notice that was an equilibrium solution right at 1. And over here, my claim is this one should be positive, which means it's increasing. This starts to give us a feel for what in the world did we actually mean when we said equilibrium solution. Well, what we mean is this is an equilibrium solution in the sense that any solution that starts out here, if v, when we feed it into our model, our original differential equation on the top, and solve it, we'll find that that function v is increasing, getting higher and higher to a height of 1. If it starts out here, the function's decreasing, the actual solution, getting lower and lower, approaching 1. So in a sense, this value attracts both the solutions on either end. What about this one? We said it was positive here. My claim is the next one should go negative, which means it's decreasing. And notice that 1/2 is a little bit different. If you're right here, you're going to the left, decreasing. If you're over here, you're going to the right, increasing. That equilibrium solution repels things away from it. This one is an actual attractor. Then continuing the pattern over here, that should be negative, which means, or hang on, I didn't actually follow the pattern. Let me start over. We had negative, that one's then positive. Let me flip that around. There we go. That one's positive, which means it's increasing. And that means this solution right here, at an electrical potential of 0, if your potential starts off negative, it increases towards it. If it starts off between 0 and 1/2, it will decrease towards it. So that's kind of interesting in the model. Doesn't yet answer part B, but this is more just our way to explain what did we mean by equilibrium solutions. They're either repellers or attractors in this model. Any questions at the moment to this stage? Yeah. Absolutely, yeah. That'd be the max and mins of the function v. So here we're looking at increasing to decreasing, a local maximum, then a local minimum, then a local maximum. Absolutely. Other questions so far? Okay, so after having done all this, well, we still need the increasing decreasing test because part B is asking for what values of V, that's a whole function and its actual potential, but for what values of V would V turn out to increasing if we solve for it? Well, it'd have to be inside here or inside here. So we can answer this question really rapidly now and say V must be in negative infinity to 0, union 1/2 to 1. So if V is in that range, then V is an increasing function. The follow-up question is essentially the same, but from the other direction. For what values of V is V decreasing? Notice the answer to getting the answer to all these questions really just involve taking the differential equation, factoring it, putting down the equilibrium solutions, and then just analyzing the sign chart. However, which way you do it is always just fine. It doesn't have to be this way if you don't prefer that way of organizing. But now once you have the sign chart for what values of V is V decreasing, we'll say from here, V must be in 0 to 1/2 union. For decreasing, could also be in this region from 1 to infinity. So that's what's going on for this kind of last question. You're not doing an action potential for an electrical neuron in the brain. I think your problem is more just analyzing a population function, which makes it maybe a little bit easier to think about what the context is doing in that kind of question. But this is the kind of algebra you would have to do in those kinds of problems. Any questions at all with the algebraic aspect? Okay, this is again a pretty slick way to do it, but if you start off the pattern on the far right end, just be extra sure it's really negative, or our whole sign chart could be flipped. And also make sure there's a power 1 here, here, and here, otherwise it does affect the pattern. It won't happen in your problem, but that's just for more other problems that could come up. Well, we did it, folks. That's modeling with differential equations. Section 9.1, again, it's a pretty light section. That means the homework is probably a really fast set as well, and nothing too major on the exams. For an exam question from 9.1, I'm probably going to ask just something generic like this once again. Example 2 is going to be a typical exam question where I give you a random differential equation, a random function. You're just checking if you have a solution or if you don't have a solution. Any last questions at all, folks, on chapter or section 9.1? Okay, let's save this up. And now we're skipping across section 9.2. It's good for just perusing of what's going on there if you're very curious about differential equations. If you're not taking differential equations, I would understand if you didn't want to read section 9.2. We're not covering it directly. But if you know you're going into differential equations, it doesn't hurt at all to skim through there. But we're going to cover section 9.3 directly. And here's how it goes. Now we're actually solving differential equations, worrying less about the geometry about them and modeling with them. We're now wanting to just straight out solve them as they come up. So these notes are going to start off as just random differential equations. But then at the bottom, if we have some time today or maybe on Thursday's class, we'll look at an honest application to separable equations. So here's how it starts. This is a whole class of differential equations where we call them separable. And if your equation is separable, there is a definite method for actually integrating these things. First of all, we have to get a handle on what we mean by separable. It means you are able to write out the derivative in an isolated way like this, dy dx, and you have function of x, let's say the g of x there, times a function of y. That's the f of y there, and they really have to be multiplying. So in other words, you're able to completely factor out the x variable or x expressions away from the y variable and y expressions. If you can do that, your equation is separable, which means you can solve that equation by the method we're about to describe. So let's give this a try out of part A. Again, kind of curious notes. There's really not a whole lot to say on these things. Really, the major thing is just how the method goes. First, observe on this differential equation, it's not even close to the right format. We have a variable y mixed together with a variable x. First thing we want to do is really make it look like a separable equation. Let's start by factoring out y squared. If we can't do that, it's not actually separable. But we're in luck here. We can take y squared, leaves behind a 1 plus x. And Newton's notation here is actually a nuisance. The problems in the book do give a y prime, but your immediate step you should take if you see it is put in Leibniz notation, dy dx. We actually need that for the method. So here's dy dx in place of y prime equals 1. So this would be our step 1. All we've done is we've factored out the variables y with the variables x. So we have a function of x here and a function of y here. Now this is where it gets really pretty weird. We hinted at this a little bit in section 9.1 because it is very weird. And here's what's going on. dy dx can be viewed in two ways. Here's the first way it can be viewed. The way we're actually looking at it, just for the moment, dy dx, that's an actual derivative. Dy dx. Dx is just y prime, which is the limit as h goes to 0 of f of x plus h minus f of x, all divided by h, where y equals f of x. So that's the standard view we take of this. This is not a fraction. It's written as a fraction just to remind us that it's the change in the y values divided by the change in the x values. So that's view 1. And here's a really, really weird view. It's a differential. So at the moment, we're thinking of it as a derivative, but we're going to go to a new equation, which is what looks identical, but it is totally different. It's an equation that contains a differential now, or a differential equation. When we say something is a differential, first I should spell it right. I forgot the L there. What we mean is dy and dx are two different variables. And algebraically, they act like variables, just like an x variable or a y squared variable, like the ones we're working here. That means we have to be mindful of our parentheses when we're interacting with them. And it also means when we go to our new equation, dx can be separated out and multiplied to the right-hand side. That's what we do when we move forward. We take the second view that we're looking at a differential. Now we're going to separate this equation. We have dy on the left-hand side, and that needs to stick with the y squared. But we have dx in the wrong spot, and so is 1 over x. We're going to move those both to the right-hand side of the equation. So now it's a differential equation. Dy dx do not have any meaning as a derivative. We have y squared dy equals multiply dx to the right-hand side, and we would have it over here, we have to divide 1 plus x on both sides. So we'll go 1 over 1 plus x. No parentheses needed this time. By order of operations, this does make sense. Well, any questions, folks, with that step there? Okay, so the method says, factor your functions as a function of y, a function of x. Factoring is not always necessary, but in this problem, we really needed to. Then literally just separate your equations. This is what made it separable. Across equality, we're organizing the y variable and the x variable, along with its components from the differential, dy and dx. We did all that work because we can view the problem in this way now. We have two integrals. One of them involves a y variable, the other involves the x variable, and we are going to solve them both. Any questions at the moment, folks, to this stage? Okay, and notice on this line, finally, this does make sense as an equation. This is why we needed dy alone on this side, because we're integrating y squared with respect to y, is what the dy is telling us. So we get a third. Y cubed on the left-hand side is going to be equal to antiderivative of this one. These are always a little bit tricky. Anyone happen to recall what would happen to that one as an antiderivative?
Natural log of 1 plus x squared?
Absolutely. So natural log, absolute value, 1 plus x. So if it had power 2 in the denominator like this, it would have been something different. We would have used the power rule instead. But as a power 1, yeah, absolutely. This one's a natural log. If this one had a 3 in front, we would just put a 1/3 in front to counteract the chain rule. But if it's a 1 plus x, differentiate this. 1 plus x goes in the denominator without absolute value. You'd multiply by 1 plus x through the chain rule, but that's a derivative 1. So it tells us we have the right thing. We'll add a constant to this. Really, there's a constant of integration on the left-hand side. There's a constant of integration on the right-hand side. But what we traditionally do in this situation is imagine we subtracted the constant over here and consolidate it on the right. So that's what we'll do each time when we do this kind of equation. Finally, because we're solving the differential equation, the goal is to solve for y. So let's triple both sides. We'll get y cubed equals 3 natural log of 1 plus x plus, well, recall, this is a constant of integration. It means that is any real number whatsoever. And if you put down 3 times c, that's still any real number. So just to keep the differential equation solution from getting too algebraically intense when it's not necessary, we would say something like this. C1, where C1 is 3 times C. This is a stylistic choice. The author does use this in some of their solutions, but then I noticed in the back of the book, they just use C everywhere. So if you left your problem as C, knowing that 3 times any number is still any number, and you left it that way, that's okay too. But if you take an official differential equations class, people are picky on this and opinionated. You want to find out from your instructor if they want you to put down this paper trail or not. It's not completely standard, unfortunately. We're just about there, folks. Last thing we've got to do is just, well, take the cube root of both sides. So we'll get y equals. Cube root is nice. There's no plus or minuses that comes up when you do that algebraically. So either put out a big parenthesis with a power of 1/3, or if you want to make it look more impressive, the radical symbol is definitely kind of neat. So there's our cube root. What goes inside is 3 natural log, absolute value 1 plus x plus C1. So that is the solution to this original differential equation from right up here. If we wanted to, we could actually verify that, but sometimes this is a lot of algebra to actually verify this one. You'd have to square your solution, x times the square of your solution, then multiply by the derivative of your solution, so we'd have to differentiate that as well. And that could be a fantastic amount of work. So usually we don't do the check on these kinds of problems. Just try to go careful in the process, and you'll be in a better stage. Well, any questions at all, folks, with this one? Okay, so this is the world of separable differential equations. In fact, we solved this type of problem before in 9.1, and that was this equation. This one was also separable. What we did was we moved, let's see, P requires P to be on the left. So we left P with dP over here. Then K was just a constant, but we needed to move dt on the other side. So it merged over here. Then we just integrated both sides. That's exactly what we did on this problem on the notes right here. So several equations come up all the time. The model for exponential growth, exponential decay, that's this one, is a separable equation. So we keep learning more and more about this kind of function, where this is the thing that came up in college algebra, and now we just learn more about it the more calculus you take. Well, we're just going to practice more of these kinds of equations. Then in example 2, we're going to switch gears and look for particular solutions. For example, this one is a family of solutions indexed by the constant C1, which could be any real number. But sometimes we want one particular solution that solves initial conditions. So we'll look into those in example 2. But for the moment, let's practice a little bit more with these. I think I have some kind of wild-looking equations. These ones are kind of tough because the variables are non-standard. We're used to x's and y's. I am too, I get it. But in applied problems, we have to get used to all sorts of different letters since that's more routine. So this is a common one that you're going to see in the homework where it's a bunch of different kinds of letters you're dealing with. First thing we want to check is everything is fully factored. Can't do anything in the numerator. But for the denominator, we could factor out an s. Let's make that our first step then. dv ds equals s plus 1 divide by s times v plus 1. So now we have functions involving only the variable s. That's going to get tied together with ds, excuse me. And we have a function involving only the variable v that's going to get tied together with dv. That kind of informs our next step. But by the way, color coding does help quite a lot with this. If you feel like you just see it better with color coding, no harm in bringing extra pencils like that to exams as well. That's absolutely welcome. So let's carefully make this work. Multiply v plus 1 to the left-hand side. So this will turn into v plus 1 dv. It's going to be equal to, for the sake of visualization, I'm going to put this temporary mark right here because we just multiplied it on both sides. But now we have s plus 1 divided by s. And we're multiplying ds onto the right-hand side. So that's what the next step would look like. Just imagine all variables going to one side, everything involving the opposite variable on the opposite side. Does that look right to folks to this stage? Okay, we've successfully separated the equation. Now, all we do is we integrate it. But I don't really like the integral on the right-hand side. That one is not so nice unless we do some preliminary algebra to it. So let's rewrite the right-hand side as s divided by s. So this is just going to be a 1 plus 1 divided by s ds. So if you just have one term in your denominator, it's easiest to integrate by just dividing everything by that one term, giving that result. On this one, we can just integrate right now. It's ready to go. Antiderivative of v will turn into v squared over 2, or a half v squared if you prefer, plus v. And now if you integrate like that, this suddenly kind of looks wrong in a certain sense because I did not put down my constant of integration. But again, traditionally, we put down one overall constant on just one side, typically the right-hand side, once we finish off all integrals. So it's okay to use the notation a little bit and leave off the constant here. So still, we're just copying 1/2 v squared plus v equals, now finally, we're integrating the right-hand side. This is going to turn into s plus the natural logarithm of the absolute value of s plus the constant c of integration. So finally, all integrals are solved. We put it in at that step. Well, any questions, folks, so far? Okay, we have a solution. There is some downsides to the solution, however. This is referred to as the implicit solution to the differential equation. Well, why do we say that? Well, let's compare it against this solution. That one's an explicit solution in the sense that we solved for the variable y itself. It's been isolated. Looking down here, we could solve for the variable v, but it's not a fun process. What we would have to use is probably the quadratic formula, because this is not a standard factorization in any sense of the term, but it is of degree 2 in the variable v, so we could solve it if we really tried. The book would never do that, though. That's just a little bit too much writing. Something like this, where the variable v is in multiple places, we can't combine it, we can't cut down the power down in a reasonable way without quadratic formula, essentially. We would always just leave the solutions like this in implicit form. So watch out for these. I think there's exactly one in section 9.3 homework. Let's take a look at the notes. In section 9.3, it says on exercise 7, leave the solution in implicit form. So it looks like that happens on problem 7. But for all the rest, you can solve for your solution explicitly, solving for the variable y or the variable v. So exercise 7 is like this one. We just leave it in its implicit form and call that the solution. Kind of unsatisfactory in a way, but you can still give some visualizations to this solution. Desmos doesn't have any trouble with it, so let's plot it and see what we have. 1/2 v squared plus v equals s plus natural log absolute value of s. No, that's not working. Let me see if I can try different variables and make it work. Let's think of that as a y and see if Desmos interprets it correctly. 1/2 y squared plus y equals, I'm going to interpret this as an x value. Looks like we're getting the right things. Plus the natural log of the absolute value of x plus some constant. It looks like it went awry right here. I'm not too sure why. So here's x plus natural log x. Yeah, that did change the shape. And I put absolute values on it. Okay, so we're okay with that. One thing I can't put in is a constant. We can put in 0, for example, or a 1. When there's a constant of 1, look what we get. Just some weird thing is emerging. We can put in a slider, say c. Then we can visualize this a little bit better. So as the constant changes, notice what happens to not the solution, but 2 solutions here. Recall, this does not even pass the vertical line test. So if we attempt to put a vertical line to this, we intersect twice. That means there's really 2 functions here. And that makes sense because if you solve this with the quadratic formula, it would go v equals some number b plus or minus, you're producing 2 functions. So whenever we get something like this, where we can't explicitly solve for v in an easy way, there is a really good reason for that. There are a lot of functions in this one implicit solution that solves the original differential equation. And just for the fun of it, let's make C a little bit weirder. So we go out here, some really weird shapes are emerging with different values of C. But all these are families of different
What happens
curves.
if you use plus C on the y side?
Oh, well, let's give that a try. That's a great question. We should get the same results, but let's see if Desmos can make that even happen for us. So let's go plus Z. Again, thanks for the suggestion on that. Add a slider there. And yeah, it looks like we're getting the same kind of stuff. On negative values this time, we're getting that weird shape. And on positive values this time, we're missing it. So same idea, but it's like a negative value being on the opposite end. Well, any other questions, folks, with dealing with that differential equation there? Okay, so again, pretty weird one. If we had an initial condition, say, for example, there's an initial statement that says that your curve at some value, maybe 5, gave you a positive number, say, that's kind of hard to hit, 0.67895, then we could actually separate it to just one function and solve for that one. But for this thing, that's a whole family of curves, and it's even worse. This is an implicit solution. So when you go to plot them, there's more than one function that you're looking at altogether. Kind of strange, but that's the world of differential equations. Well, that was so weird, but we'll try it out again. Here's our part C. Any other questions about this one before we change gears to that new one? Okay, so this one is kind of like practice doing the applied problem because of the weird variables. Maybe V is velocity, S is position. I'm not sure what the word problem would be to give us something like that. But this is now a more routine kind of a question. Variables X's and Y's. Notice we have it factored nicely on the right-hand side, but we still need to combine y4 plus 1 by dividing it off to the left-hand side. So our equation is basically separated as we look at it. dy will stay right where it is, but dx needs to multiply to the right-hand side. Let me get my colors going. So step 1, just separate your equation. That involves first dividing y power 4 plus 1 to both sides. So we have y cubed over y power 4 plus 1. dy is still on the right-hand side. Equality in the middle. Next, start writing down cosine x. Visualize dx being multiplied both sides. So now algebraically it emerges on the right-hand side of the equation. And now we're finally in business. We just need to get some integrals. Left-hand side doesn't look super friendly, but when we go to integrate that, it's not so bad. This one should be easy through an ordinary u substitution for the one on the left. The one on the right is immediate. Antiderivative of cosine is just a sine function. So let's focus on this for the moment. We have a y4 plus 1. In your denominator, great choice for u. The differential of that is going to be 4 y cubed dy. Differentials just come up all over the place. When we were dealing with this in Calculus 1, we're not doing anything too different than what we're doing with this equation. This equation here just turned into some other differential equation. And this is another equation with a differential in it. Divide your 4 out, you have a fourth du equals y cubed dy. We in fact do have y cubed dy, so this portion right here turns into a quarter du. The denominator is just u itself. So with that u substitution, maybe we'll go towards the right. I think that might make sense. Our integral becomes 1/4 antiderivative of 1 over u du. Antiderivative of cosine x dx. So all I've done on this step, following the arrow, is just use the u substitution on this integral here. That's what it turns into before we go to do the next integration. Any questions, folks, with that step?
All right, well, Greg, you said that you do in fact have a 1/4. What were you talking about?
Let me see here.
From the DUs. All right.
Yeah, I'm not too sure. I think I lost my train of thought on that one as well, but thinking about it again, from the 4 here, we would have to divide it out to get 1/4 du. And then that whole 1/4 du right here is replacing the y cubed dy.
Okay.
I'm not too sure where the thought was going, but it's probably something along those lines there. Other questions so far? Okay, now that we get to that stage, we just have a fourth. Antiderivative of 1 over u is another natural logarithm with the absolute value of u. This one was always pretty immediate antiderivative. That's just a sine x. Derivative of sine is cosine. And we'll add our constant c. Well, we're not done with this one. It still keeps on going. The next immediate step we should take is we need to fix that our solution is not for u, it's for y. So we need to resurrect y, come back over here and plug in y power 4 plus 1, undoing the substitution. So now it's a fourth natural logarithm. Y to the fourth power add 1 is always a positive quantity. So it's up to you, but you could drop your absolute values right here. So y power 4 plus 1 goes in for u is equal to sine x plus a constant. Now that we have both problems in this one view right here, notice we are essentially stuck right here because it's just too much very, very tedious algebra to feed that into the quadratic formula and get solutions to it. But over here, this is a case where we can get the solution explicitly. The reason is the natural logarithm of y is a 1-to-1 function. This will have a unique solution when we solve, but a function u squared is not 1-to-1. It fails the horizontal line test. That's why we're having trouble solving this one. It really has multiple solutions. So coming down here, if we're going to solve this equation, first thing we should do is eliminate the coefficient. Let's multiply both sides by 4. Natural log of y power 4 plus 1 is now 4 sine x plus a new constant, c1. We'll say c1 is 4 times c, the old constant. Next, we have to undo the natural logarithm function. So we use the inverse function. The inverse is the base e exponential. It'll go here, and the left-hand side is now an exponent. Natural log y power 4 plus 1. This side is now an exponent as well. We'll go e to the power of 4 sine x plus the constant, whether you call it c1 or c, you're doing the right steps here. Next, we have a cancellation going that way. That's a pair of inverse functions, so they just wipe each other out, so they're gone. We have y power 4 plus 1 equals, we don't have a cancellation here, but we can help out our constant. We can say that this is e to the power of c1 times e to the power of 4 sine x. Then on our next step, we can just say that this is a new constant. Let's c2 be e to the power of c1. We're just about there. Next step is subtract 1. Y power 4 is equal to -1 plus, you could leave this as e to the power of c1, which is okay, or you could give it the shorthand c2. Notice this is actually important to have a paper trail, though, if you went this route, because e to the power of c1 is strictly positive for any choice of your arbitrary constant c1. So c2 is not your ordinary constant of integration any longer. This is a non-negative, non-zero constant at this stage, due to the way it emerged, the exponential function. So -1 plus c2 coming from here, e to the power 4 sine x. Now that's an even exponent, so when we go to take the fourth root, we in fact have a plus or minus that emerges in this situation. We'll say that this is equal to y equals positive or negative of the fourth root of -1 plus c2 e to the power of 4 sine x. And I'm noticing in my penmanship here, that does not quite look right. That was a breakdown of notation. Thanks for anyone who spotted that one right there. Sine x is multiplying 4. It's in the exponent position. So let's put a really fast correction on that one. It should be written in this way, 4 times sine x. I'm not super picky about that. I wouldn't start nickeling and diming you on points for something like that. But that would have been a massive confusion if we were doing something further with this equation. We might have forgotten sine was in the exponent spot. So good to be really careful as you go. And let's make that just more clearly, a fourth root. Let's see if I can fix my penmanship just a little bit more on that one. Usually you want to make that slightly smaller, jam it into the crevice when you wrote the radical sign. So there's a lot of solutions here, but if you want to plot it out, you could use Desmos. And this is the explicit solution to that family of solutions. Again, that's a pretty wild differential equation. Differential equations that come from applied setting, however, can get messy like this one, so it's not too out of line. Any questions at all, folks, with that third one down? Okay, well, we're doing pretty good. Let's try out this next branch of problems. Looks like we may not finish off these notes today, but that's all right. We're not trying to rush through them. So on Thursday's class, we'll finish off section 9.3, begin working in section 9.5. Those are going to be the linear differential equations. But it looks like 9.5 won't make it to exam 2 officially. We're not going to finish it on Thursday, most likely. But continuing on, here's our new situation. It says solve the initial value problem, but the reason we're calling this an initial value problem as opposed to a differential equation is, well, it still is a differential equation, but that's the initial value. This time we're not looking for a family of solutions indexed by a constant like C2 here. We're looking for one exact solution that also satisfies that information. Y at 4 must be equal to pi over 4. But it starts off the same kind of way. We first want to separate the equation. This one's a little bit oddball. Y prime should be replaced with Leibniz notation, dy dx. Let's make that our first official step. 2 squared of x times dy dx is equal to cosine squared y. So now that we have that out, let's analyze the situation. We have a y variable on the right-hand side. That's a bit awkward. We need to divide cosine squared then to get it on the left. And that means we're going to multiply dx on the right side, divide by 2 root x as well to get it on the right side. You don't have to do it in that order. Some people might decide, well, hang on. Yeah, you kind of do actually, because you don't want to divide by dy. If dy is in a denominator, we have no notion of integrating something like this. dy must be in a numerator algebraically before we slap an integral sign on it. So let's make those steps happen. On the left-hand side, we're dividing by cosine squared. So 1 over cosine squared. That's not actually the best function to put on there, but we'll correct that on the next step. 1 over cosine squared dy is now equal to, let's divide both sides by 1 over 2 root x. That makes it emerge over here. Multiply both sides by dx, so it emerges over here. And looks like we're in good shape for integrating. On the right-hand side, that's actually kind of a nice antiderivative. Doesn't look friendly at first, but recall a super common shortcut for the derivative with respect to x of square root x is that it's always 1 over 2 root x. So if 1 over 2 root x occurs and we're taking the antiderivative, that's automatically just root x by this formula here in pencil. But the left-hand side is not as friendly. We would never want to integrate 1 over cosine squared y. That one needs to be changed out for something. Anyone see what we need to put in here by the red dot? It is a trigonometric identity, but we're not putting in like a sine function. So even though cosine squared is equal to 1 minus sine squared, that's not going to help us too much either. We need something else there.
Is 1 plus cosine of 2y?
Well, I'm not too sure about that one, but the secant squared is a good idea. If you have the reciprocal of cosine squared, it is just a secant squared. And I think the secant squared is a good way to go because that one has a quick antiderivative. So I think that'd be the great approach. I'm not too sure on the other way you mentioned, that could work out as well. I'd have to think about that one. But let's go with a secant squared. I always forget which pen I'm using here. There we go. We have secant squared y dy. Again, we like that because the antiderivative of secant squared, that's just a tangent function, equals 1 over 2 root x dx. Now we're well positioned to just integrate both sides of these. On the left-hand side, secant squared turns into just tangent x.
Y.
Sorry, say again?
Y.
Oh, thanks for spotting that. Yeah, absolutely. That variable always causes me trouble. If it's y on the left, it should stay y in the antiderivative. Thank you. Then antiderivative of 1 over 2 root x, that just is a good old root x. Finally, we put in our overall constant of integration, c. Well, we can solve this, but this is a good spot to pause right here. Recall, this is an initial value problem, and oftentimes, not always, but oftentimes, the moment you put in your constant of integration after you've solved all your integrals, this is the best time to actually solve for your constant of integration. So let's do it right here. So we said y at 4 equals pi over 4. I often feel like that deserves a little bit of a translation. What this is trying to express is y is a function with function notation. So that's the input variable. And this means when x is 4, the dependent variable y equals pi over 4 is what this is trying to convey. So we go to this equation and just plug in those two values. So let's rewrite this equation. This becomes tangent. The y variable we transfer to pi over 4 equals square root of, for the x variable, we're inputting in 4. Notice these are all constants. That just makes the evaluations immediate, plus the constant c. So finally, from over here, we have an equation to solve. Tangent at pi over 4 is exactly 1. So that's nice. Square root of 4 is 2. So on one last step, -1 is our constant c. So this kind of bounces all around. A 2-column system is probably a good way to organize your work. Think of your right column as where you're doing some of your equation solving. Then your left column is where your official answer is ending up. So this turns into now tangent of y equals the root of x. For the constant c, we just throw in -1. So where the red dot is, that's infinitely many different functions indexed by the arbitrary constant, which solves your original differential equation. But in this problem, we didn't want that. We wanted the one and only one function that also satisfies that initial value. Y at 4 is pi over 4. That forces the constant of integration to be exactly -1. Still, we have one more step to take. We can solve for this equation because tangent y has an inverse function, and we can now say y equals tangent inverse root x -1. And that's our official solution to the original differential equation up at the top. This one is massively hard to check because you have to put y as a function up in here inside cosine squared, do loads of trigonometry to show that this all works out. But any questions with the forward process? Yeah.
That be your tangent?
Absolutely. You could say either y equals tangent inverse, or I like the arc tangent because it's a little bit more descriptive. In other words, that's not an actual exponent by the red dot. That means this is not a cotangent at all. It's an inverse function. So if you write it this way, y equals arc tan root x -1, it totally avoids that miscommunication. So that's a great way to write it in. And in fact, a lot of calculators, computer software calculators like Mathematica, Maple, they do use that arctan. Well, any questions, folks, with that full process? Okay, I didn't ask a lot of these kinds of problems, initial value problems on the homework. I think it's only 2 or 3 of them. And on the notes, we just have 2 that we're trying to get through. This is our next one. This one looks kind of nasty. And again, the purpose of this kind of stuff when you see arbitrary variables and constants here is mainly it's trying to help us get warmed up for dealing with an applied problem. Our applied problem is this one down here on the notes. So what's going on with this thing? Well, when you look at the derivative in Leibniz notation, it tells us what our variables are. We have a variable L to go along with DL, and we have a variable T that goes along with dt. So looking at the rest of it, the only thing that's left out is K. That has to be represented as a constant, so let's say it here. K is a constant. So that helps us get started. I'm also watching the clock on this one. We've got it, oh, didn't mean to do that. We've got about 7 minutes and a little bit extra. So let's maybe do the organization, but I don't think we have enough time to finish this unless we're racing through it. So let's get it set up first. We have DL here. We need to get everything involving L. It's going to be the L squared. With dt, we look for anything involving t. That's natural log t. The constant is the one odd one out. You can leave it wherever you'd like. I think it's best to leave it just where it sits in this kind of problem. So I'll keep k on the right-hand side. If you're dealing with a constant, it's really up to you which spot you put it. So on the next step, we'll say we have dl on the left, but we have to divide by L squared. Dividing by L squared, you could, if you'd like, just say L to the power of -2. That's kind of a punchline, and it's just a better format if we're integrating that function. So think of multiplying both sides by L power -2, cancels that off, it emerges on the left-hand side with dl. That is just officially dividing by L squared. On the right-hand side, we have k, still exactly where it was, natural log t. And then we're multiplying both sides by dt. So that's what the setup would look like on this one. It's now totally separated, but we need antiderivatives for both sides. Let's make this our last step. Then we'll come back here, analyze what we did, and solve for the initial value. That's really the new thing on these problems I didn't want to run out of time on. First, antiderivative on the left-hand side, not too bad. We'll get L to the power of -1. So we multiply by that new, well, divide really by that new exponent. For the end, it's just putting a negative sign in front. Or you can put in -1 over L if you prefer. On the right-hand side, k is unaffected by integration, but we need an antiderivative of natural log t. That's the one that you can always take for granted because we showed how it goes. Well, the author did in section 7.1. He finds that formula for this thing. And it really is not the best use of our time to do integration by parts every single time this comes up. So you're always welcome to take this for granted as an antiderivative. Anyone recall what it is? The good news is it's pretty fast to come up with. Maybe we'll finish off this one right here, show what it looks like, but the emphasis is you're always welcome to take this for granted. For using integration by parts, the only option for you is natural log t. dv would be equal to dt. That's all that's left. Then on the left-hand column, we have just a function, and we need a differential. du would be 1 over t dt. On the right-hand side, we have a differential, and notice we're essentially just doing this on the right-hand side. When we come down and give that value v, we don't always write this down, but that is literally what we're doing. We're integrating that differential equation to get v below. Antiderivative of the integral of 1 times dt is just t. So if you like that way of visualizing it, it's not too different from what we're doing in this section. The author does not do that very often, so it's an analogy as well. So no worries if that just seems crazy. You don't have to copy that thought process. Finally, the antiderivative is u times v, that's t natural log t, minus the integral of v times du. Sorry, I said that weird. When we do that, we're taking t times 1 over t. You just get 1 dt. So all said and done, this turns into t natural log t minus t plus a constant. And just for their extra emphasis on this, you can take this for granted. What I mean by that is that's a good formula to put on your notes for exam 2, exam 3, final exam. That way, when this comes up, you're not too worried about it. If it comes up in the homework, you could just put in the result. So you don't have to rederive it each and every time. But that means when we go to use that, k is part of this antiderivative. Next, it multiplies the antiderivative of natural log t. Punchline is it turns into t, natural log t minus t. Then we add the constant of integration c. So that's what it would look like to that step. Next things we want to do is simplify this if necessary and solve for that initial condition. But we've got most of it done, folks. We'll finish off the solving for the constant c on next Thursday's class, move into the applied problem, and take a look at some linear equations in section 9.5. Well, any questions at all, folks, to this stage of the notes? Okay, well, we're almost done with week 7, folks. Just one more day of differential equations, and that'll do it for the week. Have a great night, folks. If you have any questions, I'll be happy to help out. Otherwise, I'll see you all on Thursday. Yeah, absolutely. It's going to be involved in the overall solution in that way. Yeah. It means it's going to look a little funky, but we'll live through it.